Much of mathematics is involved with proofs, so let's have a quick look at the topic. We'll return to it in Lecture 2. In maths, the most important results are stated as theorems. Subsidiary results are stated as lemmas. Theorems are formulated as a sequential chain of implications. So P implies Q, we've come across that in the previous module, where we have, at this time, P is a series of propositions, the premises, and Q is one or more conclusions. There are three basic types of proofs in maths: a direct proof or a proof by deduction. This is the one we'll mostly use. In this type of proof, every statement follows logically from the previous one. So P implies Q. The second type is an indirect proof or a proof by contradiction. Here we assume the conclusion to be false, and then we derive the implications from this and show that it contradicts our initial assumption. In this type of proof, we use the fact that P implies Q is equivalent to not Q implies not P. Our third type of proof is mathematical induction. Here we argue from a specific case to a more general case. This is not accepted generally as a formal mathematical proof, but you'll come across it in statistics. So there we argue from a specific case, a sample, to a more general case, some property of the population. Now let's look at an example of a direct proof and an indirect proof. We'll use this problem. If minus x squared plus 5x minus 4 is greater than 0, prove that x must be a positive value. First by direct proof, and second by an indirect proof. This is example 3 from Lecture 1. Now, if minus x squared plus 5x minus 4 is greater than 0, then we want to prove that x must be a positive value. We'll do this two ways. First by direct proof and second by an indirect proof. Remember, with a direct proof we follow logical steps. So we have P implies Q for each step. Now our starting point is that we're given that minus x squared plus 5x minus 4 is greater than 0. Remember, if we have an equation or an inequality and we do the same thing to both sides, then we have equivalent expressions. So let's add x squared plus 4 to both sides. We could use an equivalence here, but we'll use the implication sign there. So on the left-hand side, we'll have 5x, because minus x squared minus 4 plus x squared plus 4 cancel out. It's greater than, and we'll have x squared plus 4 on the right-hand side. Now let's look at the x squared plus 4. If we have x squared plus 4, well, x can take any value at this stage, but if we square any number, it's going to be either positive or equal to 0. So if x is equal to 0, we'll have 0, but any other number will have a positive number. So we can say that x squared plus 4 must be greater than or equal to 4, because x squared is greater than or equal to 0. Now, x squared plus 4 is greater than or equal to 4, and we have x squared plus 4 there. That means that follows that 5x then is greater than 4. So this is the same inequality there. We have greater than there because we have the greater than sign up here. So 5x is greater than 4. Dividing through by 5, we'll have x is greater than 4 on 5. 4 on 5 is positive, is greater than 0. So we could say that, therefore, if minus x squared plus 5x minus 4 is greater than 0, then x is greater than 0, is positive. Let's see how we do it with an indirect proof this time. Remember, with an indirect proof, our method is to go from not Q implies not P. This is a proof by contradiction. We'll let that be our Q, and this is our P. Again, we're given that minus x squared plus 5x minus 4 is greater than 0. But let's think about the not Q. Well, Q is that x must be positive, so not Q means we assume that x is less than or equal to 0. This implies that 5x is less than or equal to 0. That means 5x is the negative number. We have minus x squared plus 5x minus 4. Well, we have a negative number there, a negative number there, and here if x is less than or equal to 0, then we'll have 5x is either a 0 or a negative number, so that our function is the sum of 3 negative numbers. And this would imply then that minus x squared plus 5x minus 4 is less than 0. So we have the implication minus x squared plus 5x minus 4 is less than 0, but we know minus x squared plus 5x minus 4 is greater than 0. So our initial proposition is contradicted. Therefore, x can't be less than or equal to 0, it must be greater than 0. Our third type of proof was by mathematical induction. Let's have a look at how that's done in a little bit more detail. We have some proposition, let's call it an, that holds for all natural numbers n, for example. First, we check that an holds for n equals 1. That's our first step. Our second step is to assume that an holds for some value of n equal to k. The third step is to check that it holds for the next value up, where n equals k plus 1. And if that's the case, then we assume that an is true for all natural numbers n. So this is a simple type of proof by induction. We'll go through an example. We want to prove by induction that the sum of n integers, that is, adding up all integers from 1 up to n, is equal to n times n plus 1 on 2. We have our proposition, Sn is the sum of numbers from 1 to n, and that's equal to n times n plus 1 on 2. Let's see if it's true for n equals 1. If n equals 1, then n times n plus 1 on 2 is equal to 1 times 1 plus 1 on 2, because that's equal to 1. We've proved that. Maybe that's a little bit easy. Let's look at n equals 2. N equals 2. Then n times n plus 1 on 2 is equal to 2 times 1 plus 2 on 2. Well, that's equal to 3. And that's equal to 1 plus 2. We can give that a big tick again. Now we assume that sk, so n equals k, is true. It's sk, and that's true. We want to find sk plus 1. Well, when n equals k plus 1, sk plus 1 will be equal to, of course, sk plus k plus 1. Sk is equal to the sum of numbers from 1 to k, and then we add k plus 1. That's equal to k times k plus 1 on 2 plus k plus 1. Let's put those two terms onto a common denominator. Now we have our two terms on a common denominator. We can combine the numerators. We can expand that first term and then collect like terms. Next week we'll look at quadratic functions, and we'll see that we can easily factorise that numerator. So here we have a simplified formula for sk plus 1. Now we can see that that's equal to n times n plus 1 on 2 for n equals k plus 1. Having demonstrated our proposition is true for k plus 1, we conclude that it's true for any n. The purpose of this module was to give you an overview of different types of mathematical proof. It might be reassuring for some of you to learn that we won't be focusing on proofs and theorems in the course, but we will be coming back to the deductive method, the first method, and we'll use that to solve equations. We'll learn more about that in Lecture 2.